Hello and welcome to another lecture from my class, PSYC 440/640, Experimental Methods. It's a class that's a little bit misnamed because it's not so much about the methods of research, especially those that go along with experiments, as it is about research data analysis. Now that said, I do touch upon research methods and research design as I go, because as I mentioned way back in, I think it was my first lecture, I like to highlight the connections between how you design a study, the methods you choose, and the types of analyses that you can conduct. And anyway, as I often do, I'm beginning with a webcomic. This is from the excellent webcomic series xkcd.com. I highly recommend that you check it out if you haven't already done so. The author posts all sorts of clever comics using these simple stick figures, and they often have to do with mathematics or with research, and so they kind of seem appropriate to this class. Anyway, this lecture is called Statistical Decisions. It's not the best name for a lecture. In the early part of the class, when I'm coming up with lectures, I have to pick titles, and this one seemed reasonable enough because we are talking about making decisions, and decisions meaning decisions between different models when we compare them that allow us to evaluate different hypotheses that we might have about a particular set of research analyses. So if any of that seemed a little bit vague, here's an overview for what I'm going to try and cover today. I'm going to begin with a bit of a review, cover some stuff that I covered in the last class just to kind of get us back up to speed. Then I'm going to address answering research questions. That is how we sort of frame different questions and how we begin to answer them when we do research. And I'm going to build towards an area that I'm calling statistical decisions. And really what I'm doing here is trying to set up and introduce null hypothesis significance testing and the different considerations that we have when going forward with our null hypothesis significant testing approach to data analysis. And some of the titles for these sections are again a bit vague, but they're the best I could come up with as I was designing this lecture. Okay, so here's the review. Last time I tried to point out that when we're doing model comparisons, we have to set up models, and these models are associated with hypotheses that we have. So we might have a null hypothesis for a particular study, a null hypothesis that there are no differences on an outcome variable between two groups, or there's no correlation between a predictor variable and an outcome variable, or so on. Now this model, or this hypothesis, we connect to a model called the compact model, or model C. It's called compact because relative to the other models that we're going to look at, it's the one that has fewer or the fewest parameter estimates. So sometimes it has 0 parameter estimates, sometimes it might just have 1. The important idea is that it has fewer than any other model parameter estimates in a model comparison. Now the other model is the augmented model, or model A, and this is the model we connect to our alternative hypothesis. So that alternative hypothesis might be there is some difference between two groups on an outcome variable, or there is some correlation between a predictor variable and an outcome variable. The augmented model is called augmented because it has, relative to the compact model, more parameter estimates. It might have 1 more, it might have 2 more, but it has some amount more than the compact model does. And as I said, or as you could guess, of course, from the title, the whole idea of a model comparisons approach to data analysis is that we're comparing models, and we're asking, does the augmented model reduce error or explain variability? Those two phrases are used kind of interchangeably relative to the compact model. And in order to answer that question, does it reduce error or explain variability, we can compute various test statistics. And one of the ones that we compute, or it's really more of kind of like a building block for other test statistics, is the proportional reduction of error. The proportional reduction of error, as I described last time, is just the sum of squares error for the compact model. Subtract from that the sum of squares error from the augmented model. Compact model is always going to have more error than the augmented model, and divide that by the sum of squares error from the compact model. Put in slightly different notation, it's just the sum of squares error reduced divided by the sum of squares error from the compact model. It's trying to give us a sense of, relatively speaking, how much error are we reducing when we switch from the compact model to the augmented model as compared to the amount that we started with. And that calculation, or that quotient, can go from 0 or vanishingly close to 0 up to 100 or vanishingly close to 100. So obviously larger proportional reduction of error is better than smaller proportional reduction of error. If we shift from the compact model to the augmented model, but we only slightly reduce error, then maybe that comparison isn't particularly useful to us, and the hypotheses that are connected with them aren't particularly useful to us. One wrinkle that I introduced in my last lecture is pointing out that different textbooks, different sources will use slightly different notation when describing these types of calculations, and that can be a little bit confusing. The basic distinction is some notation uses subscripts, other notation does not. So this calculation of proportional reduction of error could be expressed sum of squares sub t for sum of squares total. The sum of squares in the compact model is often thought of as the total amount of error, minus sum of squares sub r. That's sum of squares residual, meaning the sum of squares that is residual or left over, the amount of error that's left over even in the augmented model. Sum of squares error SS sub t minus SS sub r is sometimes called SS sub m. So that's sum of squares model, as in the sum of squares reduction of error in the model comparison. Again, this notation can seem a little bit fussy. It's just a different way of expressing the same thing. I personally tend to prefer the non-subscripted notation. It's just what I'm more familiar with, but as best as I can throughout these lectures, I'll try and be consistent. So if I'm using non-subscripted notation, I'll make it obvious, and if I'm using subscripted notation, I'll also try to make that obvious so as not to be very confusing. Now, I mentioned just a couple of seconds ago that the proportional reduction of error can be thought of as a building block for test statistics. And the test statistic I had in mind was, of course, the F statistic. Now, you're familiar with the F statistic in the context of doing ANOVAs, which you've probably done for your own research or maybe for other statistics classes. And you maybe remember them, the F statistic calculation, as the quotient of the mean squares error reduced divided by the mean squares error for the augmented model, or maybe using the subscripting notation, mean squares error model divided by mean squares error residual. Either way, the important point that I was trying to make in the last lecture, and I guess I'm reviewing right now, is that same quotient, that same calculation can be expressed in terms of proportional reduction of error. And although it looks a little bit more complicated, it's kind of informative, I think, because really what we're talking about are ratios of error reduced, particularly the proportion of error reduced or variability explained by Model A as compared to Model C, given the number of parameter estimates used in Model A as compared to Model C, divided by the proportion of error remaining to be reduced or variability remaining to be explained, given the number of parameter estimates that are still available to be added to further versions of the augmented model. So as you can see from my equation at the bottom of the slide here, there are different ways of expressing the F statistic calculation, and you can clearly do whatever you prefer. I like expressing F in terms of proportional reduction of error and parameter estimates because it just kind of reminds me of what it's about. If you're more comfortable using a more traditional formula, of course that's fine. Either way, it's the same thing, which is kind of the point I was trying to make. Anyway, where we left off last time, I was using my example of a clinical psychologist who's studying a new form of treatment at a counseling center at a university, and he or she has devised a simple experimental design. Imagine that you're this person, this researcher. You have a predictor variable, which is group membership, because people in your study are assigned to either be in this new form of treatment or the existing form of treatment, or maybe a wait list, some sort of comparison group that will serve as the counterfactual. Group membership is your predictor variable or your independent variable. Your outcome variable or dependent variable is overall functioning, which we are operationalizing as score on the global assessment of functioning, the GAF. So imagine you've recruited 60 people from your counseling center, you've assigned them 30 to each of the two groups, you've followed them over time, and at some point, post-treatment or the sort of tail end of treatment, you give everyone a quick interview and measure their GAF score. And I've used this example before. If you're following along on YouTube, just continue to follow along. If you're in my class, you should have access to this data set in either SPSS form or in an Excel workbook on our Blackboard site. Last time we worked through an analysis to see whether the two groups differed significantly in terms of their overall functioning, and we worked through it in Excel, producing the individual predictions of a compact and an augmented model, the sums of squares, the mean squares, the proportional reduction of error, and so on. Plugged all that information into kind of a standard looking ANOVA table, and using Excel found the probability value, the p-value associated with our F statistic. That wasn't all that hard. I mean, really the hardest part is probably the function for getting that p-value, but it's not that hard, and you could certainly even look up that p-value in a table, or if you have any experience with ANOVA, just noting the value of the F statistic is almost 10, you would make the guess that it's almost certainly going to be statistically significant. Point is, you could do this work pretty easily in Excel, especially once you've had a bit of practice with it. And I think in the last lecture I also made gave the encouragement that you could try to replicate these analyses in SPSS, or I suppose indeed in any other statistics program. I might have also said that from my own experience learning to do statistics, it's been sort of valuable to try to do the same analyses, or roughly the same analyses, in different programs. It kind of teaches you a bit about the programs, and also teaches you a bit about statistics. So I think it's a good practice. If you're curious about how to do this in SPSS, you could use the go to Analyze, Compare Means, and choose the one-way ANOVA, and use treatment group as a factor, which is what ANOVA traditionally calls predictor variable or independent variable. And the dependent variable is going to be global assessment of functioning. And if you hit OK, you get basically the same results. We'll be talking a lot more about group comparisons, type analyses, ANOVA, factorial ANOVA, and so on in the third unit of this class. So I'm not going to spend too much more time on it right now. Just gentle encouragement to try to replicate your analyses in multiple different ways as a way of teaching yourself, and hopefully having at least a little bit of fun with playing around with statistics. Anyway, the next section of the class I'm just calling Answering Research Questions, which I've already kind of admitted is a bit of a vague kind of descriptor for what we're getting into. Really, I'm just trying to further set up and explore some of the issues that come up in null hypothesis significance testing. And the way I like to think about this is there's a basic process that we're trying to follow when we're asking and answering research questions from the null hypothesis significance testing kind of perspective. We're almost always calculating a test statistic, and then we're trying to discover its probability, its p-value, under the null hypothesis. If we wanted to put this a slightly different way, we could say, well, we're kind of asking a question: is this test statistic that we found from our data unlikely if the null hypothesis is true in the population? So is it unlikely that I would find a sample of data in which there's a fairly large difference between these two treatment groups, the people who got the new treatment and the people who did not, if in fact in the population of all possible data there is no average difference between those two groups? Is it very likely, or is it very unlikely? So of course, how can we tell how likely or unlikely a particular test statistic is, like the one we just calculated in our data set? Well, we could determine the likelihood of a particular test statistic if we considered it in the context of a known sampling distribution for that test statistic. That is, the sampling distribution that we would get if we repeatedly sampled from the same population and computed the same test statistic. Think about it this way. If we wanted to know how common a given test statistic is in samples from the population, we could just repeatedly sample the same population and repeatedly compute test statistics. So we could go ahead and gather our first sample of data, compute a test statistic, gather another new sample of data from the same population, compute a test statistic, and we could go on doing this repeatedly a very, very large number of times, each time computing test statistics, in this case an F statistic, and then creating a distribution of these values. That would be a sampling distribution of F statistics, or equivalently we could call it a probability distribution of F statistics. And we call it probability distribution because we could go all the way back to the beginning, to that first F statistic we calculated from our first sample of folks, and say how probable or how frequently did this occur in our whole sampling distribution. Did it occur very frequently or very infrequently, I suppose. Now, we could in principle do this, but it would of course be incredibly time consuming and expensive. You imagine sort of running a study at this counseling center again and again and again over a very long period of time. It's, possible in principle, but impossible in practice. As an interesting side note, I would just point out now that modern approaches to statistics, at least some modern approaches to statistics, are based on complicated simulations where you take the sample of data you have and treat it as kind of a starting point to simulate what a bunch of repeated samples from the same population would look like, and you kind of build your own sampling distribution computationally and use that to determine the probability of your test statistic. That's a kind of a new approach to statistics, which is becoming more and more popular as computing power gets, of course, better and better. But the classic hypothesis testing techniques that you learn in most stats classes, including in this one, don't use simulations because they were developed in a time before modern computing technology. Instead, they assume that a given test statistic, like the one you computed from your sample, comes from a known sampling distribution, one that can be worked out mathematically. So we can sort of work out an idealized normal distribution or t distribution. And within that distribution, we can know precisely the probability of any given test statistic. So again, the probability of your test statistic can be known within a given sampling distribution. Again, these sampling distributions are sometimes called probability distributions because they give us the probability of your test statistic if we assume it comes from this idealized, mathematically known sampling distribution. And back in the day, you actually had to look up these probabilities in the appendix at the end of your stats textbook. And I'm old enough to kind of remember doing that, kind of squinting at tables with rows and columns of values like you can see here in this rather grainy image capture. So for instance, when we're doing an ANOVA and we calculate an F statistic, we assume that that F statistic comes from a probability distribution or a sampling distribution that's called the Fisher-Snedecor distribution, and that is really the name. I just double-checked it. Now that's a distribution of all the possible values of F that will occur under a particular null hypothesis. So if we want to know the probability of a particular F statistic in Excel, what we ask for is where that value exists in an F distribution, which is the function here. And the F distribution is going to be defined by the degrees of freedom in the sampling distribution, which is why we have to give those values when we're asking for the FDist function. Now the F distribution centers imperfectly over 0, which kind of makes sense if you think about the equation to calculate an F statistic. If the mean squares error reduced is very small, if there's little error reduced in terms of switching from the compact model to the augmented model, or if the amount that is reduced is not much larger than the amount of error that's left over in the augmented model, then the value for F is going to be somewhere between 0 and 1. So that's just the nature of this distribution. It's just interesting to note that it is, unlike the t distribution, for instance, it's not symmetrical and it doesn't center over 0 exactly. It's also interesting to note that as the denominator degrees of freedom for the calculation of the F statistic go up, the sampling distribution for this statistic kind of lurches over and upwards and ultimately begins to resemble more of like a normal distribution. And this kind of makes sense if we think about how f is calculated. The denominator degrees of freedom are computed using the sample size. As sample size goes up, we know that test statistics tend to look more normal in their shape. If the numerator and the denominator degrees of freedom are equal and large, the distribution centers more perfectly over 1, and the thing looks pretty much like a normal distribution. And if you think back to that formula that we typed into Excel, you may have been wondering what that logical operator at the very end of the arguments is, true. Well, true here is just telling Excel to give us the cumulative probability, that is the area under the curve to the left of a particular value. So for instance, to the left of the value 3, and 1 minus that is just going to give us the cumulative probability of all the values on the other side, or to the right of that particular value. And by the way, if this seems a little bit confusing, that whole -1 thing, there is actually a function in Excel called f.dist.right or .rt that just lets you skip the whole business. So the area to the right, which I've colored green here to make it a little bit more visible, is just the cumulative probability for values of the test statistic that are greater than or equal to the one that we calculated from our sample data. So if we go all the way back to that question, we ask, well, how likely is this test statistic, or how unlikely is this test statistic if the null hypothesis is true? Well, here we've got a sampling distribution under the null hypothesis, and we've got some, the shape of that distribution is defined by the degrees of freedom in our calculation, and we can know the probability of values greater than or equal to the one that we computed. So how likely is it that we would get values like our test statistic, or indeed ones greater than it, if the null hypothesis was true? If the answer to that question is, well, it's not very likely, because if that area in green is rather small, then maybe that means that our null hypothesis wasn't that good a hypothesis and we can reject it. Well, if the answer is it's somewhat likely, if the green area was slightly bigger, if it was bigger than 5% of the total area, 0.05, then maybe we can't reject the null hypothesis. So if all this discussion of sampling distributions kind of has your head spinning, let's focus on the important points. The important points are that there's this process that we do. We calculate a test statistic and we discover the probability of it, or indeed of values greater than it, under the null hypothesis. Now, modern techniques for doing this develop simulations of lots and lots and lots of data sets and kind of build their own sampling distributions. The classic techniques are based on assumptions about known sampling distributions. Specifically, we assume that our test statistic really belongs in one of these mathematically worked out probability distributions. And again, that's going to be the focus of this class, because that's the most common way that most people use statistics now. That may change in the future. We may all be doing simulation studies in another 5 or 10 years from now, if not sooner. There's another interesting point here, and it's just kind of a reminder that larger samples are generally better than smaller ones for all sorts of reasons, and one of them is that the sampling distributions for them look more regular, or indeed more normal in shape. Even weird sampling distributions like the F distribution, and that allows us to more precisely estimate the probability of a test statistic. If we have a very small sample, and we know that our sampling distribution is going to be sort of rough, it's going to be oddly shaped perhaps, it's not going to give us the type of precision of estimation that we would if we had a sampling distribution based on samples which were quite large. So yet another reminder to see, to have large samples when at all possible. There are other reasons, but one of them is because it really helps us out with the sampling distributions for our test statistic. If you want to kind of visualize that, you can see how increasing the sample size changes the shape of the probability distribution for the F statistic. You can kind of see how the critical value for the test statistic, that is the value needed to be less than 0.05, goes down. It kind of gets easier, so to speak, for you to find a statistically significant effect if you have larger samples relative to smaller samples. I've tried to make a couple of them here. You can see how the green and red areas sort of shift as the sample size goes up. Okay, so let's go Back to our process. We calculate a test statistic, we discover its probability under the null hypothesis, and we compare that probability to a criterion. Again, it's most commonly 0.05 in a lot of psychology and behavioral sciences. And then we make a decision. We make a decision about rejecting or failing to reject, that is, retaining the null hypothesis. Now, part of this decision, though, has to take into account whether we're treating our tests as one-tailed tests or two-tailed tests. Now, if you've taken any amount of statistics classes in psychology, you've heard of these terms before, and hopefully you have some sense of what they mean. But take a second here and just ask yourself, what's the difference between a one-tailed test and a two-tailed test? Now, to answer this question, you may want to try to visualize a sampling distribution for a test statistic. So here, I've got a sampling distribution for a t-statistic, a t-test, under the null hypothesis. And before you get worried about the fact that I've just suddenly switched from talking about F distributions and ANOVAs to T distributions and t-tests, don't worry, because in this case where we're just doing a simple independent group comparison between two groups, a treatment group and control group, essentially, the value for the T statistic is just going to be equal to the square root of the value for the F statistic, and the probabilities associated with them are going to be the same. So for the purpose of this presentation, it's the same test. It's just a little bit easier to visualize with a T distribution than with an F distribution, for reasons that will, if they're not already obvious, will become obvious in a few more slides when I get to it. So anyway, here we've got a distribution of values for a t-statistic. It's under the null hypothesis, and we know that, of course, because the sampling distribution is centered over 0. So these are all the different values, or the probabilities, I should say, for all the different values of the t-statistic that we'd expect to see if we were able to do a very, 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 very long run of repeated tests drawing from the same population and running the same comparison. Again, so if it is the case in the population that there's no difference between two groups, that is, if the null hypothesis is essentially like a good way of describing the population, then we'd expect most of those values to be at or very near 0, as you can say here. And by the way, the shape of this t-distribution is defined by the degrees of freedom in the analysis, and that's of course based in part on the sample size. So the larger the samples that we're drawing from this population repeatedly, the more this t-distribution is going to basically resemble a normal distribution. So anyway, in this case, we're considering this t-distribution, and we're considering it from a kind of a two-tailed perspective. What that means is there is a region of this sampling distribution that includes 95% of all the possible values, and then there's another region that contains the remaining 5% of all possible values. And in the case of a two-tailed test, we take that region, that 5%, and we divide it in half, 2.5% and 2.5%, and put one of those halves at the high end of the distribution and the other at the low end of the distribution. So you can see here, for instance, let's imagine we got a test statistic for our particular study that was t equals 3.09. The probability of that test statistic in this sampling distribution under a two-tailed test is a probability value of 0.0031. So the test is statistically significant, we might say. And by the way, I guess I sort of should have popped up on this before. Here's that little note just reminding us that this is the null distribution. So a two-tailed t-test considers both positive and negative values for that test statistic. So in this case, we see that our t value that we computed in this particular sample was 3.09. We might have, if we coded the groups differently, we might have a negative value, so negative 3.09. Either way, that difference or that test statistic would be statistically significant, because the p-value that we're getting, 0.0031, is the cumulative probability of all the t-values that are going to be greater than the sort of high critical mark on the high end of the distribution, or less than the low critical mark on the low end of the distribution. Now let's consider this same sampling distribution, same t-test, same degrees of freedom, but we're going to consider it from a one-tailed perspective. A one-tailed t-test in this way can be done for only positive differences or positive values of the t-test or negative values of the t-test. And as we'll see in a slide or two, this is something that we really need to specify ahead of time. So if we're testing the comparison in a particular way such that the treatment group has better functioning than the control group, then we'd expect a positive value to be associated with the superiority of treatment group over a control group. That would be the t-statistic would go in the positive direction. So here, deliberately in this example, I've used the same test statistic, t equals 3.09, but if you look really closely, or if you back up the slide or back up the video to the previous slide, you'll see that the probability value associated with that same t-statistic in a one-tailed test is actually a bit smaller. It's about a third of the size as it previously was in a two-tailed test. With a two-tailed test, that same test statistic, 3.09, and actually technically also negative 3.09, had a cumulative probability of 0.0031. Here, the same test statistic, t equals 3.09, has a cumulative probability of 0.0015, so about a third of that former value. Now, in that sense, you could say it kind of makes it easier to detect a significant effect if you do a one-tailed test, because any given t value that you have, or any given test statistic value, is going to be less probable in a null distribution if it's a one-tailed test than it would be in a two-tailed test. You could think of a one-tailed test as being more liberal, or a two-tailed test as being more conservative. An important consideration to make here is that the one-tailed test is really testing a directional prediction. So we might predict that the treatment group will have better functioning than the control group, or we might make some sort of opposite prediction if we think that the treatment is going to be in some way damaging or iatrogenic. But we have to specify that ahead of time, and then we can test that directional prediction and take advantage of the in air quotes, or easier prospect of getting a statistically significant effect, or we could say the greater power to detect a significant effect if we're doing a one-tailed test. As compared to that, though, we could do a two-tailed test where we're testing both ends of the probability direction and making a non-directional prediction, or testing a non-directional prediction for our hypothesis. So we might say, well, we predict there's going to be a difference between the treatment group and the control group in terms of their functioning. It may be the case that the treatment group has better functioning than the control group, and of course, as clinicians or as people involved in clinical psychology, we may hope that that's the case if we think this new treatment is going to be better. But if we want to be conservative, we could say, well, it might be the case that the treatment group does better over time. It might be the case that they do worse. We're going to test a non-directional prediction that there will be just some difference between those two groups. It could go in one direction, it could go in the other. So if we don't know, or if we don't feel confident making a directional prediction, or if we want to just generally be more conservative, make it a little bit harder for ourselves to detect a significant effect, decrease our power, maybe because we're a little bit skittish about the risk of a type 1 error, we might choose to make a two-tailed test, or use a two-tailed test for our analyses. So at the risk of kind of repeating myself, I'll just say in the case of a one-tailed test, it's sort of easier to find a significant effect because the critical value for the test statistic that you need to exceed in order to have a probability of less than 0.05 will actually be smaller in the case of a one-tailed test than it will be in the case of a two-tailed test. Two-tailed test makes it kind of harder. That critical value on the sampling distribution under the null hypothesis that kind of marks out where the probability is less than 0.05, that value is going to be bigger. You have kind of a higher bar to step over or jump over, statistically speaking, I suppose, if you're doing a two-tailed test. Let's just do one more example, or look at this one more time, hopefully to kind of drive home the point. And this is going to be kind of an extreme example where we have a rather small data set. We've only got 14 people, we've got two groups, we're sort of dividing them 7 and 7, which is way too small probably for most types of research. But I did it deliberately to kind of highlight the difference that doing a one-tailed test or a two-tailed test can make. So here's our example of a two-tailed test. We've got our sampling distribution for the t statistic under the null hypothesis, and we have a particular test statistic value t equals 1.8. That's a pretty small value for t, and we might guess going in that that's probably not going to be statistically significant. And under a two-tailed test, the p-value associated with that test statistic, the probability value, is 0.095, so about 0.10. So that's clearly a higher probability than our usual threshold of 0.05. And if this was a real example or something analyses we were really doing in the laboratory, we might say, oh dear, not statistically significant. We can't reject the null hypothesis that there is in the population no difference between these two groups. So again, we wouldn't reject the null hypothesis in a two-tailed analysis. But in a one-tailed analysis, maybe we would. Same sampling distribution, same test statistic value, 1.8, but under a one-tailed distribution, assuming we predicted it would be positive 1.8, the probability associated with that value is 0.0475, so about 0.05. We might say it just kind of squeaks in under the line, and we might go ahead and reject the null hypothesis and say, there is evidence for a statistically significant difference such that the treatment group has better functioning than the control group. Same sampling distribution, same value for the test statistic, two different interpretations, and I'm not claiming that one is right or one is wrong, but the point hopefully that you see here is that it kind of matters whether we think about a test as a one-tailed test or a two-tailed test. And you may be thinking to yourself, well, how do I make a one-tailed test out of a two-tailed test? Typically stats programs like SPSS will give you by default two-tailed results for the p-values of the different test statistics you compute. Let's say you want to make a directional prediction, or let's say you really want to take advantage of the better power associated with a one-tailed test versus a two-tailed test. All you really need to do is divide the probability value of the test statistic by 2. So if p is 0.10, you just divide it by 2, and now p is 0.05 if it's a one-tailed test. And I actually remember years ago, and I won't name any names here, but it was like my first or maybe second year of graduate school, sitting down and looking through a whole raft of analyses with a faculty mentor of mine, and we were looking at a table of test statistic values and p-values, probability values, and almost all of them were non-significant at the usual 0.05 level. And I remember the faculty member saying, yeah, maybe we could just test these all as one-tailed tests. And he basically went down the line dividing all those p-values by 2 and saying, oh yeah, well now this is significant, now that's significant. That's probably a little bit of a dodgy approach. I mean, that was a long time ago, and maybe we as a field were a little bit less aware of the problems associated with that type of approach, or maybe this guy was just doing what he considered exploratory data analysis and wasn't too worried about the increased chance of false positives. But it's funny, all these years later, that example kind of sticks out in my mind. We were trying to have the joy of p less than 0.05, and we were willing to bend, let's say, if not break the rules to get there. Oh, by the way, I said that the sampling, that looking at one-tailed tests versus two-tailed tests is a little bit easier with the sampling distribution for a t-statistic. It is, because the sampling distribution for a t-statistic is symmetrical, and as sample size gets bigger, it looks more and more like a familiar normal curve. You already know, or hopefully you remember from earlier in this lecture, that the sampling distribution for an F statistic has this weird sort of asymmetrical shape. And because of the way F is calculated, the values are only ever going to be greater than 0. And so what we typically do is we think of those probability associated with rejecting the null hypothesis as kind of piling up on one end of the distribution. Now that said, an ANOVA can be done to test a directional hypothesis. Just as I did in this example with the t-test, you could do an ANOVA with just 2 groups, and you could predict that the one group is bigger than the other, or that the other group is bigger than the one. And all you would do to switch back and forth between a one-tailed test and a two-tailed test is divide or not divide that p-value. I could have used this as an example earlier, but I tried a couple times. It just looked really confusing, so I thought, I'll switch to a t-statistic sampling distribution, and hopefully that will be a little bit easier to visualize. And hopefully it was. Anyway, an important point to make here is, and if I haven't made this already really, is that decisions about the tails that you're going to use for your test, whether it's a one-tail test or a two-tail test, should be made a priori, that is, ahead of the fact, before you've gathered data, start to analyze it, and those predictions should be based on theory-driven hypotheses. You should have a strong reason to expect that the one group will be bigger than the other, or that the correlation between two variables will be positive and not negative. If that's the case, then by all means, use a one-tailed test. It's funny, for many years, I was certainly taught, and I have taught other people to avoid one-tailed tests because it's sort of easy to convince yourself after the fact, like, oh gee, I really did mean to do it as a one-tailed test. Lately I've been reading some blogs and some posts on social media where statisticians and methodologists have been saying, hey look, one-tailed tests are great if you can justify them. If you have a good a priori reason for doing a one-tailed test, they give you more power, they allow you to test a directional prediction, which is often more interesting than a non-directional prediction. So now, I've kind of changed my thinking, and I would say, yeah, don't avoid them, but be aware when you're being honest with yourself, or I should say be honest with yourself about making these predictions ahead of time if you can justify them based on good theory-driven hypotheses. Don't make these decisions after the fact. Don't post hoc decide, oh well, gee, this difference is non-significant under a two-tailed test, but really I kind of always knew that the direction would go in one direction, so I can kind of justify doing a one-tailed test. It's very easy once you have the data in your data set to say, oh yeah, I can see here in my sample that the treatment group had better functioning than the control group, and really I kind of always figured they would, so really that's okay for me to do a one-tailed test. If you do that, you're increasing over time the likelihood of making false positives. You're also just being a little bit intellectually dishonest. This is one of many different practices and procedures which are sometimes called p-hacking. That is, you're kind of hacking or fiddling with your analyses with the goal of reaching this arbitrary threshold of p less than 0.05. And that's just, well, people do it, but let me say I discourage you from doing it. Alright, so if you're thinking about one-tailed tests and two-tailed tests, it may be helpful to consider some scenarios or some examples. So try to do this. Try and play along with me as you watch this video. Imagine that you're a cognitive psychologist studying language. You're like a psycholinguist, I suppose. And you're doing a simple experiment where people are put into either one or the other of two possible training groups. So there are two levels of our predictor variable, which we're calling training. There's no training, and then there's some amount of training. And what's happening in these training groups is people are being given novel words that actually don't exist in any language, in which they could have no previous knowledge or experience of. People who do this type of research, I believe from hearing a few talks, have software that can develop these odd novel words, and you could imagine a cognitive psychologist presenting these words to people if they're in the training group and instructing those folks to memorize the words. Of course, the people in the no training group, they're just sitting there, or at least they're not being exposed to these new novel words. Then the outcome variable, let's imagine sometime down the line, a few hours later, a few days later, is the level of recall people have for these new words. Now, because they're new words, they have no previous experience, so they have no previous reason to know these words, and you can only ever remember more than 0 words. That can only ever be the case that you remember some amount of these words. And presumably people in the training group who had some exposure to them during their training session are going to remember more than the people in the no training group. So here's the question: is this a situation where we can do a one-tailed test, or is this a situation where we can do a two-tailed test? Well, you could probably go either way on it, but I would argue, or I would suspect, that you can justify doing a one-tailed test. The effect can only go in one direction. It's only going to be the case that the training group, the people who got exposure to those new words, are going to know more than the people in the no training group. I mean, it's conceivable that both groups will have an average recall of 0, but it can never be the case that the people in the no training group have more recall than the people in the training group. That just seems incredibly unlikely or almost impossible to fathom. Training can only ever increase your recall. Doing a one-tailed test makes it, again, and the kind of using the air quotes here, easier for us to detect a significant effect, a more precise or useful way of phrasing that would be to say it makes our test more sensitive to the effects that we're looking for, and maybe these training effects are really subtle. We're exploring some rather subtle aspect of the way the mind gathers and processes and stores linguistic information. So we might want more sensitivity, we might want more power to detect effects, and again, we may feel justified given our design and our methodology of saying, yeah, one-tailed test makes sense in this situation. Here's another example. Imagine you're a health psychologist and you're studying meditation, and you're doing basically the same type of study as you just saw. It's a simple independent groups experiment where you have a predictor variable that we're going to call treatment, or 2 levels of treatment. There's a meditation group, people who are given some amount of training in transcendental meditation or mindfulness meditation or something like that, with the idea of helping them relax and focus their mind. And then there's a control group, and they don't get any sort of training in meditation or maybe in anything else. Predictor variable is treatment, outcome variable is some sort of measure of psychophysiology. I'm just kind of arbitrarily, I suppose, almost picking just a heart rate is a way of operationalizing kind of stress response. People with high resting heart rate, we might assume are a little bit more stressed out than people with low resting heart rate. And of course, you're trying to see if there is a significant difference between these 2 groups in how reactive or stress reactive people are in terms of their psychophysiology. So here's the question again. Is this a situation in which we can do a one-tailed test, or is this a situation in which we should do a two-tailed test? Now, it's not like there is absolutely the right answer to this question, but if it was up to me, I would argue that you should probably do a two-tailed test here, because probably the effects can go in either direction. It might be the case, and indeed, as the researcher, you might hope it's the case that people who learn how to meditate have lower resting heart rate than people who do not, but it's conceivable that this could go in the opposite direction. Perhaps learning how to meditate is going to be frustrating for people, or it makes them feel stressed out, or they breathe in a weird and awkward way that actually jacks up their heart rate. People can sometimes hyperventilate when they meditate. Meditation could decrease heart rate, but it could also increase it. Maybe also, we want to be a bit more conservative here, because this is a situation in which we might be testing an intervention that we would use at a clinic or hospital, and we want to be a little bit hesitant about saying that meditation, yes, changes heart rate, because if we do, then people will start to adopt it as a treatment protocol, and perhaps it will be helpful, but perhaps we want to be a bit conservative before making that conclusion or drawing that conclusion. I'm sure you could maybe argue that it's a one-tailed test situation, but to me it seems like the better answer is that this is a two-tailed test situation. Okay, so after talking about one-tailed tests and two-tailed tests, I'm going to move on a little bit, and in the last section of this presentation, I'm going to talk about what I'm just calling statistical decisions. And really, what I mean by that is sort of a bit more of an introduction, a bit more of a formal introduction to different components of what's called null hypothesis significance testing. That's that familiar form of hypothesis testing that you were probably taught in other statistics and research methods classes, and you probably know some stuff about it already, but it's worth reviewing that stuff and also hopefully learning a little bit more. Now, the textbook that we use for this class kind of describes this process of making statistical decisions as sort of like a game that we're playing with nature. And that game goes something like this. Is model C, is the compact model a good fit for the data? Relatedly, is the null hypothesis accurate in the population? So we want to, we're familiar with this idea that when we do statistical hypothesis testing, we often begin by assuming the null hypothesis, assuming that there's no difference between groups in the population, or no correlation between variables in the population, or essentially no effect in the population. We want to make a decision or make a guess. That's how the game goes, but the only information we have is data. We have data from our sample. We don't have the whole population, so we have to sort of make an educated guess or take a risk based on the sample that we've drawn from the population. By the way, that's why I'm trying to kind of pictographically represent here with these little marbles on this slide and on the previous slide. All the marbles in the bag are the entire population of data for whatever it is we're studying, but we only ever get a small group of them, a small sample of them, and we need to use that information from that small sample to make a decision. Again, we're using data to make an educated guess, but there are different possible outcomes for that guess. We could make a correct guess, so that would be something like we reject the null hypothesis when we should. It is the case in the population that there is an effect. There is a difference between two groups, or a correlation between two variables, or so on and so on and so on. And we, based on our sample of data, arrive at that same impression. So we say, aha, let's get rid of this null hypothesis that we had previously assumed. We're going to reject it. And that was the right call. Or it could be the case that based on our sample of data, or I'm sorry, it could be the case that in the population there really is no difference between groups, or there's no correlation between variables. Essentially there's no effect, and based on our data that we have, we don't have insufficient evidence to reject the null hypothesis, so we continue to maintain it. So we don't reject the null hypothesis when in fact we should not reject the null hypothesis. Either way, that's a correct guess, or a good call. The other types of outcomes, of course, are errors. So we might make a false positive, or a type 1 error. We might reject the null hypothesis when really we should not. We claim, based on our sample of data, that there is an effect in the population, a difference in groups between in the population, but really there isn't. Or we could have a false negative, a type 2 error, where we claim that there is no difference or no effect in the population based on the data we have, but in fact there really is, and we missed it. So a false negative. If you've taken any other stats classes, or indeed if you've read the text for this stats class, you're familiar with the type of four-square table that people sometimes write to illustrate how this would work. There is the reality of either the null hypothesis being correct or incorrect in the population, and then there is the decision that we make to either reject the null hypothesis or not reject it. And that kind of defines in this four-square two correct guesses and two types of errors that we could make. Now in psychology, we're probably most familiar with the type 1 error rate. That is the probability of making a type 1 error. Probability here is defined from kind of a frequentist perspective. So we're imagining that if we repeatedly sampled the population and conducted the analysis, whether it's a t-test or a regression or an ANOVA or whatever, we repeatedly did this over a very long number of times. What are the number of times, what's the frequency within that run where we would make a type 1 error? What's that probability from kind of a frequentist perspective? This is called the type 1 error rate, or the type 1 error level, or it's sometimes just called alpha level. And again, you've encountered this before, and you probably know that it's set usually by researchers at this sort of arbitrary threshold of 0.05, where there's like a 1 in 20 chance that when we reject the null hypothesis, we shouldn't have, because in the population there is no effect, or there is not the effect that we are claiming. As a little bit of a historical side note, I was going to make a slide or two about this, but this lecture is already rather long, as I'm sure you've noticed. Where did this 0.05 come from? Well, it was actually first proposed by R.A. Fisher, one of these founding figures in the history of statistics, and he was really clear that it's nothing special. Like, there's nothing special about 0.05 as compared to any other criterion, and he's tried to, in his writing, de-emphasize the use of it, but because it provides such an interesting and kind of easy binary decision, less than 0.05, reject null hypothesis. Greater than 0.05, do not reject null hypothesis. Researchers for generations now have really seized on it and have almost kind of made it canonical in psychology and other behavioral sciences. And really, that's probably not the best way to think of it. It's just a value. It's just who was it? Was it Jacob Cohen? Oh, I forget, or Rosenthal. This will come to me, but one famous researcher once quipped, isn't it the case that God loves 0.06 almost as much as 0.05? The implication being that we become a bit fixated on this one threshold, 0.05. And I would argue, and other people smarter than me have argued, that we in general are overly fixated on type 1 error to the detriment or to the exclusion of other considerations. For instance, to the detriment or to the exclusion of thinking about type 2 error rates. This is the probability of making a false negative judgment over a long run of repetitions. This is called type 2 error rate, or type 2 error level, or sometimes just called beta level, which gets a little bit confusing when we get to the unit on regression, because there are other things called beta in the world of statistics, at least the world of applied statistics. This level of beta is usually calculated by the researcher for a given level of alpha and a given effect size. Now, in the next lecture, we'll spend a lot of time sort of dwelling upon the interrelationship between type 1 error rate, type 2 error rate, effect size, sample size, and statistical power. But suffice it to say for right now that we usually calculate beta based on a fixed idea of what alpha should be and a guess at what the effect size is in the population for whatever effect we're studying. Now, Jacob Cohen, the famous statistician, suggested that we have a level of power of no more than about 0.20, so no more than a sort of a 0.2% chance, or a 20% chance of not rejecting the null hypothesis when we should, or falsely failing to reject the null hypothesis, committing a false negative error. By the way, this link down here is a link to G-Power, a free power analysis software that I'll be talking about a lot more in the next lecture. And if you're in my class, I link to it on Blackboard, but you've maybe heard of it before. If you haven't, you can follow that link, or just go to Google or whatever your preferred search engine is and type in G-Power, all one word, and you'll probably get the link that you need right there. So again, I say we in psychology, and this is a criticism that I'll make, but again, smarter people than me have made, we often focus too much on type 1 error rate. We maybe ignore or don't bother to ever calculate our type 2 error rate. We often don't spend enough time thinking about effect size. And really, there are different types of effect sizes. All of them, and we'll talk about some of them in this class, are just standardized ways of measuring the magnitude, or the size, of course, of an effect. And they're calculated in a way to be unit-free, and to give us a sense of the quantification of how big or a relationship is. So, think about it this way. If you're doing an analysis where the predictor and outcome variable or variables have a natural metric that is well understood, you may not need an effect size. So in class, I often use the example of trying to predict people's level of sleep disruption from their level of alcohol use. Imagine you're a sleep disorders researcher, and based on abundant literature that drinking tends to disrupt sleep. And you might also be aware that people who sleep poorly might feel motivated to drink in a sense of wanting to medicate and help themselves fall asleep. So you might well predict there's a relationship between these two variables. Now, if you operationalize drinking as number of alcoholic drinks consumed per week, and you operationalize sleep disorder as like number of hours slept per night, lower numbers being worse, higher numbers being better, or like number of times awoken over the course of the night, higher numbers being worse, lower numbers being better, then you've got either way, variables which have a pretty easy natural metric. We all know what one drink is, and we know that that's not as much as 2 drinks and not as much as 4 drinks. And we all know that 6 hours of sleep is different than 4 hours of sleep. In such a case, you might find, I'm just guessing off the top of my head, that for every additional drink that people have, their sleep in terms of hours per night declines by 20 minutes, let's say. That relationship can be discussed pretty easily without recourse to any sort of effect size calculations. You could calculate effect sizes, but you might not need to. On the other hand, let's imagine you were trying to look at the relationship between self-esteem and eating disorders symptoms. Well, self-esteem is an abstract construct that can be measured using various self-esteem measures like self-report questionnaires. Just the eating disorder symptoms. Eating disorder symptoms might be a list of symptoms, or it might be might be measured on a scale that tries to quantify how bad your eating disorder is, and you might predict that there's some relationship between these two variables. The problem is neither of those two variables have obvious natural metrics. Like if someone has a 2 on the self-esteem scale, that sounds bad because 2 is low, but how bad is that, or what does that really mean? And if someone has a 12 on the eating disorder symptom scale, is that a lot? Do they have enough symptoms to be diagnosed, or are they at danger for injury or death? You might not know naturally what those means, and so you might feel motivated to compute an effect size to kind of represent how big that relationship is, so that someone reading the paper or looking at your poster or just hearing you discuss this at a conference might say, oh yeah, okay, it looks like there's a big relationship or a strong magnitude of relationship between these variables. So again, effect size, and really there are different types of effect sizes, are all meant to kind of quantify those types of relationships. So some common types of effect size might be things like Cohen's d, which is often calculated when we're comparing means of two groups in kind of group comparisons type analyses, like doing experiments and then doing t-tests or ANOVAs. Pearson's r, the familiar correlation coefficient, is itself just a natural effect size, and so we know that a correlation of 0 is quite small. A correlation as it gets closer to +1 or closer to -1 is bigger. So if I say, oh, the correlation between someone's self-esteem and eating disorder symptoms is -0.7, the higher their self-esteem gets, the lower their eating disorder symptoms get, and that correlation is about 0.7. You might say, well, that's pretty big, because it can only ever go up to -1 or +1. There are other ones out there, Hedges G, omega squared, different sorts of odd ratios and risk rates if we're thinking about logistic regression. You don't need to know all of them, but depending on the type of research you do, you may find yourself using one or the other more frequently, just because they're easier, or they're somewhat easier way for you to communicate information about the magnitude of effects. Now, Jacob Cohen famously came up with one of these. Actually, I think he came up with more than just one, but the famous one, I suppose, or commonly used one, is Cohen's d. And he, in his writing, provided some kind of interpretive guidelines. So, like a Cohen's d of 0.02 is considered a small effect, and a Cohen's d of 0.05 is considered a medium effect. And so, as much as he kind of argued that you could use these labels to kind of give a qualitative name or qualitative descriptor to a quantitative value for an effect size, he cautioned against over-reliance on these canned, as he called them, effect sizes. What we really should be doing is considering the effect size in terms of the practical context of the study. And there may be situations in which even relatively small effects, as we quantify them in terms of effect size, might be important. A common example in research methods textbooks is like the research on daily low-dose aspirin for heart disease. In some of the research, at least a couple of the pieces I've dug up over the years, the effect size for how much taking aspirin every day decreases your risk of heart rate is tiny, like it is microscopic. That means for most people taking aspirin, they're literally wasting their time. It will do nothing for them. However, low-dose aspirin is well tolerated by most people. Aspirin is cheap and generic and easily available, and if you're the lucky person for whom it has an effect of reducing your risk for heart disease, then it's well worth your time. So, small effect size, important finding, and one that probably many people, probably I should be doing this at my age, take. So it depends on the context. It's not just about finding a number and saying, oh, that's a big effect size, or oh, that's a small effect size. So again, we probably don't think enough. I should say we probably think too much about type 1 error rate. We probably don't think enough about type 2 error rate. Probably don't think enough about effect sizes, and we probably don't think enough about power, which is defined as the chance of detecting an effect when one is there. If there really is a difference in the population, a correlation in the population, a whatever, what's our likelihood of being able to detect that? Being able to reject the null hypothesis or model C when really we should do so. We can calculate power different ways. It is, by definition, 1 minus beta. So if you're not making a false negative, you must be making a true positive. So with Cohen's guideline of 0.20 for beta, we get a power of 0.80, so an 80% chance of detecting, of rejecting the null hypothesis when we should. Again, this is something that Cohen argued should be our goal to shoot for. And we can sometimes use calculations of power We sometimes do them after the fact or post hoc to see how much power our analyses had. We sometimes do them a priori or ahead of time to see how big a sample size we need or how big an effect size we need in order to have as much power as we want. So in the next lecture, we'll play around a little bit with G-power and consider some a priori and some post hoc power analyses. Anyway, I've mentioned this guy a couple times already. I've probably mentioned him in previous lectures, but just Jacob Cohen, famous statistician and researcher. He wrote one of the most important books, for kind of applied researchers, people like me and others, in terms of using multiple regression correlation analysis. He wrote books about effect sizes and meta-analysis, and he wrote books and papers about power, and really argued that we should be paying a lot more attention to this stuff than we really do, or at least than we commonly do. And with that inspiration, I'm going to try and emphasize that in the coming lectures for this course. So okay, review, we're almost done, and again we're clocking in at over an hour. Man, these are long lectures, so if you have the stamina, good for you, because I am tired. Anyway, what have we learned? Well, we learned a little bit about research questions and this idea of the model comparisons approach, framing research questions as comparisons between models, each model being associated with a particular hypothesis, and comparing models in terms of which one reduces or which one is associated with less error and which one has more complexity, using those two criteria to evaluate whether it makes sense to reject the null hypothesis or abandon the compact model in favor of the alternate hypothesis and the augmented model. I also, in a somewhat haphazard way, I worry, introduced some other concepts and ideas which are important for statistical decisions, things like test statistics and sampling distributions, tails, and things like effects, error, and power. So a lot of stuff got covered today, and again, if you have the stamina to stick with it the whole way, good for you. Preview of next time, well, like I already said, we're going to be looking at power analysis in greater detail and playing around with G-power, so that's going to be interesting. And I'll probably start to talk a little bit about some of the assumptions that go along with some of the statistical tests that we'll do later in the semester, kind of jumpstart that part of the conversation. Alright, so like I always say, thank you so much for your attention. I know it's a lot of time to sit here and listen to me. If you have a chance, make yourself a cup of coffee, cup of tea, and kind of perk yourself up a little bit. If you have questions and you're in my class, you can ask me over email or in class or on Blackboard. If you're not in my class and you're just watching this video on YouTube, you can post comments in the discussion or in the comments area, questions in the comments area. I'll do my best to be vigilant, and if I see those questions, I'll answer them as best I can. So thank you very, very much, and I'll be back with another lecture, well, pretty soon. Bye-bye.